It's kind of hard to come up with a name for this section. It's loosely based on Chapter 3 of the Alcott text. That will give you the relevant kind of overarching background information. But really, I want to summarize this chapter with the question, where does it all come from? Where does it all come from? You might be surprised that I'm digging as deep as I am here. But what I want you to be able to do eventually is consider some object, like the plastic housing of this pen, for instance. Or I've got a metal nail. Come on. Stop hiding. Here's a simple nail. Right there. Nailed it. So these objects here, I want you to be able to, in your mind's eye, envision the big blasters and movers digging out iron ore, crushing it, going through some process to make the ore easy to handle, and then going into a blast furnace, and then being poured into these giant train cars that go to the casting house, and then cast this into a long cylinder billet that then gets drawn into wire and then goes through a stamping machine to turn it into a nail, and then gets packaged and shipped to a hardware store, and then some guy buys it named Dr.Ray. And so the life cycle of the material from the ground to now gives you the power of seeing. It's like I have historic vision. I can see in my mind, all the way back to where it came from, and I can envision all the processes and all the properties that were given to that material along the way. It's good in a couple ways. It gives you the ability to do failure analysis. If it fails, why? What could have gone wrong? Well, maybe it was step B or C or step Q, because I know step Q. Right? So that gives you the power of understanding it. This plastic housing on this pen, can you envision an oil well drilling down and tapping some underground oil deposit, and that getting sucked out and distilled into vast numbers of different compounds and organic molecules based on carbon, and then those getting shipped to some Dow or DuPont or some other company that polymerizes base polymer, and then that gets sold or made into pellets that then go to an injection molder that then injection molds this housing out of whatever this is, LDPE, calcium carbonate filled LDPE. Good year, yeah. So that's what we're making this out of, based on crude oil or natural gas. You can also make polymers out of natural gas. Did you know that? Pretty cool. And so then this gets eventually thrown away or recycled and turned into other stuff. So that gives you the ability to understand from the beginning to the end these processes. It's powerful. Use it. Embrace it. So if we were to classify the main topics, minerals, oil, and living things, are where everything comes from. Minerals take a few different paths. So a lot of the earth is silicates. We'll talk about that in a moment. But metal oxides, carbonates, that can be compounded, meaning we just crush and mix it, and then it can be heat processed into a ceramic. That's one option. Less manipulation. There's still some high temperature work there. It still requires chemical processes, if you will, but not as many as metals. If you take those same oxides, you can also reduce them with high heat or lots of electricity, which also produces high heat. Separate their constituent elements into the metallic form, and you can make metals and semiconductors and all sorts of purified components like silicon and iron, aluminum. Okay, that's minerals. Oil. This crude oil, what's that stuff? We'll talk about that quite a bit. But It gets purified. It's a mixture of just everything. And it gets separated out into all these different molecules that then can be used for pharmaceuticals, drugs, cosmetics, plastics, paints, coatings, shoes, tires, on and on and on it goes. Crude oil would be a completely different world today if it weren't for crude oil, let alone just all the transportation from gas and energy. But just the product, you know, we wear it, we walk on it. It's the carpet and our shoes. We walk on it twice. So it's crazy. Crude oil, it's everywhere. Yes, it can also be cotton and living biopolymers as well. Can be, but usually not. Usually it's polyester, man-made rubber soles of our shoes. Living things, some processing, wool, cotton, leather, wood, the wonderful world of the rendering plant, industrial products from leftover parts. It's a big topic. We're not going to go in full depth there. I don't think you can handle it. But there's lots of examples of biopolymers and interesting materials. So, here's a nice third grade textbook diagram for you. The Earth's crust. So the Earth, of course, has a lot more mass that we never tap into. You know, what if we drilled for iron like we drill for oil? You just got to go a few hundred miles deeper. I struck iron! Man, is it hot. It's like a volcano, because it is a volcano. Bad idea. Be an interesting business model, though. I'm going to drill so far down, I'm going to extract iron and nickel from the molten core of the Earth. It's a bold plan. Yeah, it would melt everything. All your equipment would just be immediately destroyed, but it would make an awesome movie.
Assuming you could even do it, you also destroy the magnetic field.
If you sucked all of it out, which I don't think anybody ever could. But you could try. It'd be like an eggshell, right? It's like, oh no, we might. Anyway, we'll try not to turn this into a cartoon, but you can imagine what would happen. Typically, we are only interacting with a couple of miles of the Earth's crust. And so everything you've ever touched, likely, is derived from often not even a mile deep. It's just stuff from the surface. But there are some deep mines. If we were to take Earth's crust and look at its chemical composition, first we're looking at compounds, you see that 50% is silica, silicates, silicon dioxide. 50%. That's a lot. So the sand, rocks that just have lots of silicates in them. It's all over the place. Alumina is next. You see it makes up about 15% of the continental crust. Calcium, magnesium, iron, sodium, potassium, even water. You might say water? Yes, water. Not as liquid water, but as water trapped in a crystalline lattice. Solid, entrapped water of crystallization is what's being described there. Water that is associated with the mineral in a crystalline lattice. CO2, titanium, phosphorus. Anyway, so there's the standout list of what is it, 10, 12 different compounds. Now, look at that list. Now let me ask, what one element do you see most often up there? Oxygen. It's in every one of them. Holy cow! So most of Earth's crust is oxygen. Wait, I thought the oxygen was like what we breathed. Well, yes, it's 21% of what we breathe. 78% is nitrogen. If we didn't have nitrogen in the air, we would be hyperventilating all the time. You ever seen somebody hyperventilate? We breathe in a bag. I'm not really prone to that, but we would, summer camp, people would like overdo it and freak out and pass out, and they'd be over there breathing in a bag or something, playing soccer. Not Dr.Ray, I'm built like a tank. But we need that nitrogen to dilute down the oxygen, makes it more comfortable and useful to breathe. It would also things would spontaneously combust way easier in 100% oxygen. So not only does it make up our atmosphere, it's also trapped in the very dirt that we walk on all the time, and also creates a problem. And that is, in the ores that we mine out of the earth, such as this very heavy magnetite iron ore, it's iron mixed with oxygen. And it is a really heavy rock for what it looks like. We'll pass that around eventually. Rock out! So, iron ore. Iron and oxygen. But look at our pie chart. Now we're just viewing it based on the elements. Half, roughly, is oxygen. A quarter is roughly silicon. And everything else is wedged in little Pac-Man's mouth there. And the remaining 25%. Aluminum, iron, calcium, sodium, potassium. That's a short list compared to that table up there. And so that starts to give us a picture of the natural abundance of the stuff in our world, and how everything else you have ever heard of is in that 0.8%. That's kind of sobering. That's an interesting thought. Wikipedia saves the day on that, because they have a great representation of natural abundance using a logarithmic chart, and allows us to much more greatly expand the visualization of the list. So these rocks that or these elements are what really are called the rock forming elements, and so the ones that are just so common. Keep your eye on how they are calibrating this list. Abundance of all the different atoms using per element of 1 million atoms of silicon. Or 1 million, per 1 million atoms of the element silicon, everything else on this table exists. They could have used oxygen, but using oxygen, I guess, was a little bit uncomfortable as a standard, so they took the most common metal or metalloid and made that the benchmark. So using a million silicon atoms as the benchmark, how does everything else pan out? Well, you can see that we've got the transition metals kind of cluster in here: nickel, chromium, zinc, manganese, iron pops up as being pretty common. But so, kind of middle of the road in terms of being common. Then you have what we often call the rare earth elements, but they're not as rare as some other metals. But they aren't super common, but they're about the same as the transition metals. You see them here. But then you have the really rare ones, and these are the ones that really set the price lists for economies. Things like gold. See gold, platinum, iridium. Look at iridium, rarest. Iridium is uniquely dense and hard material. They use this for reflectors and solar panels and space mirrors, and they use it for some pretty expensive materials. Iridium is a very unique metal. Osmium, very dense, very hard. Most common use, it's kind of out of style, but pen nibs, ink pen nibs for the dip in the ink and write, like your Continental Army or something. Those had osmium, very hard metal plating that allowed it to stand up to lots of friction, essentially. But rhodium, ruthenium, palladium, these are catalysts that can be used to catalyze chemical reactions. These often cost thousands of dollars an ounce. Expensive stuff. And it's quite rare. And that's why. So, elemental abundance explains part of what we observe. Why some metals are worth mining, why some aren't. If we look at the sources, turns out some of these show up as oxides, but some of them show up in many other forms. So, commercially viable oxides, you see those in brown. commercially viable sulfides. We see those in yellow. So remember from 135, maybe your professor talked about that, but the halogen family is right next to the chalcogen family. Not they don't always mention that, but chalcogen is a Greek word which means ore formers. So oxygen and sulfur being the most common of the chalcogens, form ores. There they are. Metallic ores are often found as oxides or sulfides. Some of these elements are derived from salt. Seawater actually is a common source. Salt mines, salt flats, you can mine them, such as Utah has a lot of natural salt deposits, but they're halides, sodium chloride, sodium fluoride, sodium bromide, etc. Phosphates, often find phosphorus-bearing rocks filled with lanthanides, carbonates, magnesium, calcium carbonate. Calcium carbonate is a very common rock. Got a big chunk of limestone here. If it's just calcium carbonate, you call it lime. If it's a calcium magnesium carbonate, you call it, anybody know? Probably not. Dolomite, common rock. You kidding, Dr. Ray? I'm going to just pull dolomite out of the air? I don't know. Maybe you're into it. You know, some of you go to rock concerts. You know where Dr. Ray goes? Rock shows. There's a group of people that know how to have a good time. Party on. I got lots of samples here that I bought at the Eau Claire Regional Rock Show. Happens every year. Hey, did you hear the Stones are coming to Eau Claire? No way! Mick Jagger? No! The Eau Claire Regional Rock Show! Ha ha! So, Stones coming to Eau Claire. I'll let you know when that comes to town again. I know a lot of you want to go, blow your paycheck. It's tempting. It's really tempting stuff. So, specimens from all over the world, right? Anyway, so we've got all these different sources, the rocks. For those that they care, which is maybe 2 people, there's actually entire global associations devoted to each metal, because for some people this is their business, this is their life. And so all things copper, the Copper Development Association. A lot of great resources of how the copper infrastructure works. Let's say you want to know about chromium. Well, here's the site for you. Wake up. Oh, come on, the Chromium Association went out of business? Oh, those are some good people. The vanadium producers. Anyway, each metal has its own supply chain and infrastructure from the ground to intermediates to uses. Think about that. We're not going to go into great detail in each one. My point here is mainly to get you to recognize and think about from raw material to intermediate. We're supplying raw materials, but also some people live their whole life making good money off of material supply chain. A lot of engineers work in those areas. So I'm trying to sort of paint the picture of all the different possibilities that are linked to these topics. So how do we get, question?
Actually, I had a question on the previous.
Yeah.
I noticed that all the radioactive elements, including technetium, is one of them, is not there. I was wondering.
Yeah, so if you look at the table, 89, 90, 91, 92, and then everything like goes into ghost mode and it's all outlines. The reason for that is that all of those are synthesized by some atomic method. And so those are all manufactured elements. And as you see, people finished out the bottom row there from 93 to 103, and then they've finished all the way out to number 118. They filled the octet of that final set, and now everybody's waiting. Is somebody actually going to, jump the shark and find a way to make number 119? I mean, can you feel the suspense? It's electric. I mean, are they going to be able to do that? Because that's a huge energy jump to do in these particle accelerators. I mean, they make sometimes one atom of these elements. One atom! By taking two heavier nuclei and counter-propagating particle accelerators, and then they align it magnetically so they smack together and then blow up. And then they measure the energy of that explosion. It's kind of small, but kind of not. It's amazing the energy you get out of one atom when you do this. But then they can energetically prove that that element must have existed for, a good 3 milliseconds before it exploded. And then they discovered it. They try it again. If they can reproduce it, they report it, and eventually it gets some unintelligible name, named after some person that's dead long ago, but made important contributions to science. I'm kind of making fun of it, but like LV is named after Lawrence Livermore Labs, is the guy and the lab in California. Many different scientists who were instrumental in, like Seaborgium, number 106. He was a guy that was instrumental in making new elements by these methods. Rutherforium, dubnium, borium, hassium, meitnerium, all these guys were important to atomic theory, quantum mechanics, and making new elements. And so they're immortalized now with their own element name. So uranium, we'll talk a bit about. It doesn't make it onto the commodity-based element list just because it's important for nuclear energy and for atomic weapons and for tank munitions and really hard bullets that are very controversial from Iraq War and lots of other things that uraniums contribute to. Fluorescent glass, radioactive orange paint that people used to use for some unknown reason. So that's the reason that they're not on there, is because most of them are man-made and they have sort of fringe uses. But that's a good observation there. Yeah, so also number 43, that noticeable omission from the table. Notice that our major source just kind of like didn't touch. It's like, we're just going to skip over that one. Think how technetium feels about that blank spot right there. You kidding me? You could have just said man-made. Don't just like erase my face and just leave a hole there. People just always discriminate against technetium. It's just not right. But yeah, right there it is. It's because it's man-made. So they're mostly looking at natural sources of the elements. So see how that works? Because at this point we're thinking about from the earth, from the rock to the product. So there's some specialized things that we're not talking about. Other questions? Rants about certain elements you have a lot of emotional attachment to? No? Yeah.
How come? I thought it was pronounced technetium.
Well, Dr. Ray is not always the best linguist. Technetium, technetium. Technetium does sound a little bit more professional, doesn't it? I'll have to dig a little deeper. You could be right. So maybe we should take a poll. No? Yeah, I'll look into that, though. Good point. Well, let's talk about smelting. I thought I smelt something in here, said the person that works at the blast furnace. So smelting is the process of extracting a metal from its ore. Okay, smelting. The gangue, not pronounced gangue, it's pronounced gang, is a commercially worthless rock that accompanies an ore. It's called gang. You remove the gang from the ore. Imagine gang wars at these rock shows. So gang, the worthless part of the ore. So the process of smelting, you have to melt that down and separate it from the commercially important part. So it's often necessary to use a flux, much like the flux that we used in making glass this week in lab, but now it's for a different purpose. Or for a related but different purpose. So often limestone is the cheapest form of a flux that's effective at melting silicates. So if you dump into a blast furnace iron ore and coal to make carbon monoxide and limestone, a few things happen. The first thing that happens is the limestone helps dissolve and glassify the silicates. And the glass is less dense than the molten metal, and so it rises to the top as slag. The whole purpose of adding limestone is to make slag from the silicates that are so prominent in the crust, they have to be removed. And so adding limestone helps melt it out. It's counterintuitive that adding a rock like this, limestone, will help melt the silicates, but it's true. Just like the powdered rock that we put into our crucibles, silica, soda ash, and limestone. Soda ash would be even more effective, but it's more expensive. They can take limestone and just dump it in, and it works. And they don't really care about the slag, although we will talk a little bit more about slag later on. Riveting lecture. But you have to remove the gang. So here we see the dense tin oxide nodules, crystals, intermixed with the silicates. I've got a good example of that right here. Some of my, as you surmised, rock show specimens here. Come on. So up in the north part of the state, also in the Upper Peninsula, the UP of Michigan, there are a variety of copper deposits. And so this is what the rock would look like from the outside. Kind of a slight greenish color, which is a clue to what's inside. See that white band of silica in there. So somebody took a rock saw, and sure enough, there are metallic veins of copper in this rock. Look at that. Straight up metallic copper. Before smelting. And look how the silicate is formed and intercalated right into that pocket of metallic copper. Then we have two different oxidation compounds of copper, the light green, the dark green, malachite, and something else of copper oxide, but it's all mixed in. Now they sliced that and then put a lacquer on it so you could see the beauty of the sample. This sample had a different treatment. On this one it got tumbled mechanically and beat on until the non-metallic part chipped away. But look at how we still have sand, giant inclusions of silica, just still encrusted right in there with this prickly metallic copper. So copper is unique in that you can find native copper veins with metallic copper. Gold, of course, you can find gold nuggets. You can find silver, you can find copper, but those are exceptional. The noble metals, copper, silver, and gold, can be found in the environment as metals. Everything else only exists as oxide. So I'll pass these around. I know you're just waiting to get your mitts on these. But take a look at these and think about the fact that that came out of the ground. And I think that one is a superior, from the superior area, the one that's sliced and lacquered. So the gangue versus the ore. So some different oxides: tin, cassiterite, copper, cuprite, malachite. Cuprite, that's the other one that's in that rock. I think the light green is cuprite, the dark green is malachite. Lead oxide, hematite, Fe2O3, magnetite, Fe3O4. I'll pass around a magnetite later on. Some different sulfides: copper, lead, mercury, galena, cinnabar, chalcocite. So these are the raw materials from which we get some of the most commercially important metals. We're not going to go through each of these steps, but just think about all of the processing that is required: the sorting, the crushing, the separating, there are a variety of ores that benefit from a process called flotation. Because the silica and the certain other carbonate compounds are more water-loving than the metal oxides themselves, if you've crushed the mineral, mix it with a proprietary surfactant, a special soap, you can make the more water-loving ore, the gangue, sink to the bottom, and the metal-rich particles will ride air bubbles to the top of a flotation cell. They then skim off that froth and dry it down, and it turns out that differential sedimentation by flotation is one of the most effective ways to separate things like copper ore from the silicates. And so it's literally like bubbling in your milk, except with purpose. And by skimming off that froth and drying it down, they can isolate copper. Thickened, filtered, dried, and finally an ore concentrate that's then advanced to the next step. You'd have a mess on your hands if you were trying to smelt the original ore. Lots of waste, slag, and just garbage. So by working through this process, you've made the smelting operation far easier. And every ore has some variation of this theme. It always looks something like this for everything, from the raw rock to an ore concentrate. So then how do you get it to be reduced? Well, for iron, it's as simple as heating it in the presence of fuel with limited oxygen. Think about the logic here. Maybe you are into tuning engines. You understand the idea of a fuel-air ratio, right?
Yes.
You have too lean or too rich of a composition. That has certain symptoms and certain performance issues with a motor. It needs to be tuned. Choke the engine at the beginning to get lots of fuel, to get the fuel throughout so that then you can start a cold engine. That's not where it runs efficiently. More fuel to air. Well, in the event of trying to smelt a metal, here's what you do. You get a fuel source, and it's super hot. It wants to spontaneously combust, but then you limit the amount of oxygen so that it says, hey, there's plenty of oxygen in here. It just happens to be in a compound with a metal. Why don't we just rip away that oxygen? Okay, but it's going to cost you. It's going to cost you 2 electrons, or 1, or 3, depending on the oxidation state. And depending on the thermodynamics of the system, often, no problem. It donates the electrons from carbon, in this case, to the metal, so it can rip away the oxygen and make carbon monoxide / dioxide eventually as a byproduct, because carbon monoxide as a gas, entropically and enthalpically, is more favored than the oxide. It lowers its overall energy by doing this. So using the oxygen from the metal oxide as your oxygen source is really the heart of the smelting operation. And so when done properly, at the end, you would have molten iron at the bottom, often a layer of melted slag on top of that iron, so you tap it down below the slag level, and then you're going to blow off carbon dioxide off the process as a byproduct of the coal that then stole the oxygen from the metal. Genius. Now this is done in a highly automated way these days, but it can be done in a very low-tech way. The bloomery furnace. This is the way the people for thousands of years have been doing this. You build a clay rings up into a stacked furnace, dig a little hole, you have a bellows so you can force the air at the right rate into it to make it very hot, and you stack in charcoal and iron ore. You light that up, you heat it for 5 hours. It's a laborious process, but when done properly, you will end up with iron underneath a layer of slag that you can then dig out, chip off the slag, and then this big iron blob could then be worked by a blacksmith into all sorts of things, from shovels and tools to pickaxes, swords, brackets, harnesses, parts of plows, you name it. That's the way it was done. So this is, though, inefficient. And so there needs to be a way to automate this. There's some other iterations that have been done. I had a student once says, yeah, I watched this documentary on this Quest for Solomon's Mines was the name of this PBS documentary, and they archaeologically uncovered some of these melting pots where they evidently were forcing people to work on foot bellows all day. And they would stand 4 people around this boiling cauldron there, and they would have to work the bellows to force the air. Doesn't really sound like a good internship opportunity, does it? That'd be a rough job, for sure. But that process of forcing the air, it was a known process for smelting copper or silver or whatever. They were working in that central furnace area. But interesting, 1,000, 2,000, 2,500-year-old technology to get the proper fuel-air mixture to smelt metal. Literally, what we're looking at here. A lot of these operations here in Wisconsin are kind of, I think there's still some ore shipments that come out up there and they barge it down to Chicago or out to the Atlantic or whatever. But a lot of this metallurgy operations from northern Wisconsin are not quite in their heyday anymore. But they're certainly still up there. Deposits of iron and copper. And anybody from up in that area? Anybody? No? Usually there's a few people in each class that are like, yeah, I'm up here. I just would love to go tour some abandoned mines. It just sounds awesome, right? It's like free time with Dr. Ray. Hey, you want to go get lost in a mine? How about Tyler's Fork this time? So, I don't know. Sounds kind of cool. But iron mining, Wisconsin's not a stranger to that. So, how's the process done? Well, like we said, ore plus fuel plus air. It's called pyrometallurgy. So what we'll have to do is on Monday we're going to spend a deep sea dive into the iron process. We're going to look at how blast furnace work and then carry forward. So get a start on that homework. Did everybody get a copy of the homework? Or how many people still need a homework? So I can bring it